The sun is a giant burning ball of gas. It's so big that roughly 1 million Earths could fit inside the sun. But in physics, we pretend the sun is just a single point mass. That means we pretend all of the giant mass of the sun is located at a single point, the center of mass. But the sun is not alone in this solar system. There are planets, including Earth, which is spinning around in an orbit about the sun. It might seem odd that the Earth is moving around a circle. After all, if the sun weren't there, the Earth would just go in a straight line. Why would the Earth go in a straight line? Because of Newton's first law. Newton's first law states that when an object is moving, it just keeps moving at a constant velocity unless an outside force acts upon it. Here's a scene from the movie WALL-E, where WALL-E is out in outer space, and look at how he just keeps moving across the screen. And the only time he finally stops his motion or changes his motion is when he feels an outside force from the fire extinguisher. Here's another good example. Watch what happens once the teacher pushes and lets go of the bowling ball. The bowling ball moves across at a constant velocity because there's no unbalanced force acting on it. So it just keeps doing what it's doing. It keeps moving in a straight line. Now you might be wondering about the force of gravity. Well, the force of gravity is balanced by the normal force, so those cancel out. And then you might also be wondering about friction. Well, there is actually friction, but we're ignoring it in this simple scenario. To make an object deviate from its path, like to make an object move with circular motion, requires a force. So let's watch what happens when you push with a perpendicular force. Notice that this person is always pushing the bowling ball in toward the center of the circular path. The direction of the force is in toward the center. So back to the Earth. As it moves around the circle, something has to be pushing it toward the center of its circular path, toward the sun. As the Earth moves with the velocity directed this way, it feels a perpendicular force. Where does this force come from? The Earth is out in outer space. Nothing is touching it. The answer is gravity. Newton's law of universal gravitation states that every 2 point masses in the universe, m1 and m2, feel a force of attraction that is proportional to the product of their masses, m1 times m2, divided by the square of their separation distance. That is Newton's universal law and law of gravitation, and we can express it using this equation right here. If we change it from a proportionality to an equation, we simply add a constant, that's big G. Big G is called the universal gravitational constant, and the value is given in your data booklet. This might sound crazy. Newton basically said any 2 objects you choose in the universe pull on each other. So your left hand is pulling with a gravity force on your right hand, and your head is pulling with a gravity force on your feet. Everything pulls on everything else with gravity. You can even see that on a small scale. We've got 2 big bowling balls here, and in the middle, this rod is connected to 2 little spheres. The rod is suspended above the ground by a tiny wire, and it's laying horizontal, so we're looking at this from above. These little marbles are attracted to the bowling balls with gravity. And watch what happens when this time-lapse video is sped up. You can actually see the entire rod twist because these little marbles are attracted and pulled by gravity toward the bowling balls. We can take this idea that Newton proposed, this law of gravitation, and apply it to spheres by treating them as point masses. So here are 2 spheres with masses m1 and m2. If we pretend they're point masses, then we're acting as though all of the mass is concentrated at the center. And so the distance that you need in the denominator, the separation distance, is the distance between the 2 centers. So you would add the 2 radii plus this value d. This might be a weird idea, but we explain it in physics using the notion of a field. we say that there is a gravitational field filling all of space, empty and filled, and the gravitational field is what does the pulling. So now let's figure out how to test the gravitational field. Let's say we've got some big mass m, like maybe it's the Earth. And we're going to choose a point in space. We can use a small test mass to test the gravitational field at the point we choose. So here's my test mass, little m, and I'm placing it right here at this location. The test mass m would feel a gravitational force F due to the source mass. So this mass m, this guy over here, is attracted with some force F. We define the gravitational field strength to be the force per unit mass on a small positive test mass. The letter G represents gravitational field strength, and the equation is F divided by m, and this is very, very similar to the equation for electric field strength. What are the units for gravitational field strength G? Well, the numerator force is newtons, the denominator mass is kilograms. Let's take this mass big M again, maybe it's the Earth. And instead of testing just one point, I want to test many points. First, I'll choose this place right here, this spot. I test the field by putting a small test mass right here. And that small test mass is pulled with a force in toward the center. If the force on the test mass is this way, then so is the gravitational field strength. That's a rule. The G vector is always in the same direction as the direction of the gravitational force that the test mass is feeling. So the test mass would be pulled in the same direction as the G vector. If I take this point, where would the test mass be pulled? To the right, attracted. And if that's where the force is directed, then that is also where the gravitational field strength is directed. If we choose this point, the gravitational field strength would again be toward the mass big M. If I choose this point, we're still being pulled with a force to the right, and so G is also still to the right, but the force is smaller, and therefore G is also smaller. We could fill the entire space, and you get a picture looking something like this. Now, we don't really draw this picture the way I'm showing you right now. Instead, we connect all of these lines, and we connect them all so that it forms field lines like this. The field lines point toward the mass, and they end on the mass big M. This idea of a single source mass is really important, and we have another equation we can write down for the gravitational field due to a single source mass. First, we imagine that source mass big M. To test the field strength, you have to have a test mass, so let me get a test mass, little m. That test mass is some distance r away, and it's attracted with a gravitational force F. The force is given by Newton's law of gravitation, and there it is. It's the product of the two masses divided by the distance squared times this constant. But wait a second. Gravitational field strength is just force divided by the test mass, little m. So at this point, we have our test mass, little m, right here at this point. And so at that point, the value of G is simply, well, I can plug in for the numerator. I can plug this expression in for the numerator. The little m's cancel, and we are left with gm over r squared. That's the equation for the gravitational field strength due to a single source mass. And again, this is very similar to an equation that we learned when doing electric fields.